All right. Welcome back, everyone. Very excited to have Zongyi present. Guess great to see you again. You presented in my SciML series, so very excited to hear about your work on neural operators. So, Zongyi, over to you.
Thank you, Kartik and Ventek. Thanks for inviting me. It's very happy to give a tutorial on neural operators in the Michigan Summer School. So this talk is going to be two parts. For the first part, we're going to cover a general introduction of operator learning and the neural operators. We'll show a little bit of the neural operator library as developed at Caltech. For the second part, if we have time, we're going to discuss some of the recent work on general model and foundation models, especially the scale consistency neural operators. Okay, so I think many of the physics and engineering reduce to partial differential equations, and the main motivation of our line of work is to solve for partial differential equation efficiently and accurately. Just a very little bit of introductions. For partial differential equations, there are many examples. For example, there are initial value problems. So given a small domains, we can solve how, for example, heat diffuse into the space, which is the initial value problem. So given the initial conditions, we can solve for later times, for example, time equals 1. There are also coefficient problems. So given different type of material contained of two type of medias, we can solve for the pressure fields on this domain. So in this case, the input will be the coefficient function A and output is solution function U. And in many cases, we can convert such a problem into an input-output map, and we can solve it with a standard supervised learning settings. Existing solver, such as finite difference, finite element, finite volumes, usually require to first discretize the space into a finite space, then solve as a linear system or other linear methods. For example, the most elemental finite difference methods is to approximate the gradient on a grid, and then we solve a linear systems. The gradient is approximated by the neighbors of each node. These finite different methods, they have been developed for like 50 years or longer. They're nice, but overall, these methods can be slow for complex problems. For nonlinear problem, time-dependent problems, usually we need to discretize the space into a very, very fine grid, like 1,000 by 1,000 grid, and then 1/1000 time steps. So in this case, the overall computation could be very, very slow. That's why we want to have a machine learning methods to accelerate this process. And more importantly, we want to have a more general models that's not only solving one type of equation or one type of boundary, but it can be trained on more diverse data sets and generalized to general settings that we can utilize data more efficiently. Overall, we can divide the machine learning methods into several categories. So on the left, we call it operator learnings. So that's a solve for a class of equations, say the heat equations or the Darcy equations. And it can be working on this type of equations with one type of input. The variable could be the initial conditions, coefficient, or boundary, or geometries. And the hope of foundation model is to take more general class of inputs. On the right, we have a solver type or say function type of models that solve one specific equation at one time. So in this case, we're just modeling one solution functions or say one domain at a time. In this case, we have to solve one instance by one instance, and it could be slower but more accurately. So there is recent work that combine general solvings and specific solving for a solver. And in this work, we're going to zoom into the operator learning parts. First, defining learning solution operators and introduce several models that learn the underlying solution operators. Right. Operator learning, it just means that given underlying equations, for example, initial value problem or coefficient problems, we define this problem as an input-output map. In this case, the solution operator F, it is basically the inverse of the finite difference matrix, or it's the inverse of the matrix in the linear system. And we're learning reduced order models that given the inputs can immediately predict the outputs. So compared to solving one equations, the operator learning is solving a class of equations. It finds the solution operators of the underlying equations. It's more like a standard supervised learning settings in machine learning context, where fix and underlying equations and gather data sets of multiple training instances, and then learn the map in the supervised learning settings. And in many cases, we have to gather the data sets using existing solver. That's why we motivate to have a more general models that can use existing data sets, even for a slightly different equation or different condition or boundaries. So compared to solving one equations that discretize the spatial domain, learning an operator is to discretize the function space. In this sense, the input functions contain all type of inputs, for example, all type of input coefficient or all type of initial conditions. And this map will try to match the input function space to the output function space. But of course, the function space in general could be infinitely dimension space, and we want to have some expansion of the space that is efficient, be modeled by a finite number of parameters in machine learning models. So later we're going to talk about Fourier embeddings and other models that have a nice decay of this approximation of function space. And one more words about numerical solver versus data-driven methods. Usually we consider numerical solver as more general. It can be work for many different parameters. They have worst case guarantee and consistency. But in general, data-driven methods, they trade accuracy for speed. In general, they are much faster as we don't need to resolve gradient or solve the linear system. But usually we don't have a guarantee even if we have many very, very fine grade. But this consistency maybe can be defined regarding the number of data and the size of models. But hopefully, if we have a good enough data and large enough models, the error can converge to zero. And after this problem is defined, we need to consider the best models for operator type learnings. Because the underlying problem is not a vector to vector mapping, but it's a function to function mapping. We need to consider the best discretizations. If we use a fixed discretizations, say 64 by 64 grid, then such model cannot be applied to other datasets with these different discretizations. So one consideration is to have a general discretization-free models, or we call it resolution independence discretization convergence models that can be applied to a wide class of discretizations that is tailored to the functions, not to the vectors. And another example is that if we learn convolutions in convolution neural network, usually convolution neural networks, they're great to capture local patterns. But for partial differential equations, many cases like Poisson equations, will have global features. So usually we need to combine local filters with global filters that can be captured the global effect of the solution operators. Okay, so that is a definition of the operator learning problems. Basically, given a partial differential equations, we define the solution operators as the inverse of the differential operators. And we want to learn it using a supervised learning settings as machine learning models. And to learn such models, the general idea is to generalize from a standard neural network to continuous settings to functional settings as neural operators. Usually we consider a standard neural network, feed-forward neural network, or called multi-layer perceptrons, as a stacking of linear layers with activation functions. The linear layer is just matrix repetitive multiplications, and activation functions are ReLU or GLU or some simple pointwise nonlinearity. Generalized to the function settings, now the linear matrix vector multiplication now becomes a linear integral transform. So we will define a kernel function kappa that is corresponding to the weight matrix in the linear transform. And now this linear operators is defined as a linear integral transform respect to some kernel function kappa. There has many implementations. One way is to implement this integral transform using a graph neural network. Another way is to project both functions and kernel into the Fourier space. Then we can parameterize this kernel functions using Fourier coefficients. In general, this is one class of methods. We're going to learn linear integral operators. Even one linear operators cannot capture solution of nonlinear equations. We can stack linear operators with nonlinear operators. And if we have a deep models of many linear and nonlinear layers, such models will have the capacity to learn nonlinear and non-local transform for Navier-Stokes and complicated equations. Indeed, our group has been improving approximation bound, generally saying that for any continuous operators defined on the compact subspace, there exists two-layer neural operators that can approximate it. So this approximation theorem is very similar to the approximation theorem of functions of multi-layer perceptrons, but we generalize the theorem to a function space. And for specific equations, such as Navier-Stokes equations, usually we can bound the number of parameters for the model. But usually the proof is based on mimicking existing solvers, such as pseudo spectrum solvers, and to get the number of parameters inside the solvers. And we can show that machine learning models can, in some sense, implement pseudo spectrum solvers, and we can bound the number of parameters in that. And in general, the nonlinearity is also very important. Even we project to some fixed space, for example, PCA space or Fourier space, it's very important to have a nonlinear decoders that decode the fixed spaces to adaptive basis for the problems. And there are also theory work showing that nonlinear methods with nonlinear decoders can be efficient than just linear decoders with fixed spaces. So for the implementation of neural operators as integral transform, one line of work is use graph methods. We call it graph kernel methods and the multi-scale multiple graph kernel methods. They basically define the integral as a sum of neighbors, as a graph message passing aggregations. And there are many similar work, for example, Mesh GraphNet, learning to simulate complex phases from the DeepLine team. And they also have GraphCast. They have a different starting points, but the resulting models become similar. And the idea is we need to define the graph message passing as a continuous integral. So the graph need to be defined respect to the integral of a ball, not just nearest neighbor connections. In this sense, the graph layers can be viewed as a continuous integral transform, but restrict to a ball. Another class of operators is encoder-decoder operators, or in some sense, it can be called a reduced order model. For example, in PCA nets or depot nets, so given the input functions, we will first project it to a fixed number of bases, a linear subspace, and then we will learn some functions f in the linear Euclidean space, vector space, to the output vector space Rn. And after we get these spaces, we will project to the output space V. This is also a very general architectures. In machine learning, we have encoder decoders, or uh, uh, say GANs type of models. They all encode the input functions to some fixed dimension subspace, and then learn the mapping in the fixed dimension subspace. And the group of Andrew stores actually have some theory to consider the relationship between numerical solvers and this type of reduced order models of machine learning models. Indeed, they are very similar. In some sense, we need to find bases. These bases could be a finite element basis or polynomial basis, or in the machine learning model, we have the PCA basis or neural network basis. Overall, for the infinitely dimensional problems, we need to find some finite dimension subspace that can capture most of the information in the function space. Right, so to recap, there are two classes of transform. One class is based on integral transform that makes some change at each layers. Another class is reduced order models that project to the implementation space inputs to some finite dimension subspace. Both are there are many works for this class of methods, but we will going to focus on the first class where we learn integral operators. Okay, so for the next part, I'm going to introduce neural operators based on the Fourier interpolations, based on the fast Fourier transform. The idea is if we just do the integral transform, in general, it take n square number of points, which can be kind of expensive. So one approximation is to put the input function and kernel both to the Fourier space based on fast Fourier transform. So in this case, my input functions will be taking a Fourier transform on the Fourier space, and we're going to do the integral transform on the Fourier space. And based on the convolution theorem, convolution in the spatial domain is equivalent to a pointwise multiplication on the Fourier space, which makes the implementation even easier. So the overall architecture is just first do a Fourier transform and then multiplication, in the end, inverse Fourier transform. So in this sense, the kernel function kappa will be leave to the Fourier space and it becomes this Fourier coefficient R. We don't need to parameterize this kappa explicitly, but this kappa kernel function will be parameterized by a matrix as a weight matrix on the Fourier space. Right, so the overall architecture is just 3 steps. First, taking Fourier transform, and then linear multiplications, and in the end, the inverse Fourier transform. Usually, we will truncate to a finite dimension Fourier basis that is shared across a class of equations. This truncation can be viewed as a denoising or as regularizations. Or we also have adaptive Fourier neural operators that does not explicitly truncate, but as a thresholding to zoom out some lower frequency. So this design of neural operators, it can be applied on any kind of resolutions. So say given a resolution 100 by 100, we will take it to the Fourier space and make some pointwise multiplication on each Fourier modes and transform it back. It does not depend on, say, 3 by 3 kernels, which the respective perspective fields will change according to the overall resolutions. And we also add some machine learning tricks, some considerations. For example, we have the skip connections, accept alongside the Fourier space. So the spatial skip connection will capture non-periodic and non-smooth functions, while the Fourier parts will capture periodic smooth convolutions. So in this sense, it will not just be limited to periodic or smooth problems like traditional pseudospectrum methods. Any questions so far for the models?
Yeah, good so far.
Thanks. Yeah. So on Caltech side, have been applying on several different applications from weather forecast to carbon storage and fluid and solid mechanics. Just overall, we find out that just like other machine learning models, if you have a big data and big models, usually we get the advantage of using a data-driven machine learning models. One example is the weather forecast. So thanks to the European Central Weather Group, we have the large Era 5 datasets. And recently, NVIDIA team also have a called the same weather forecast datasets that contain even larger datasets. So for this kind of models, we can train adaptive Fourier neural operators given the weather in the history and predict what happened in the next 6 hours. Let me show one example. So this is NVIDIA's virtualization of the weather forecast models called ForecastNet based on adaptive Fourier neural operators. It can correctly project the trajectory of the 2016 Typhoon Matthew. And this has been a continual work that there many recent development happen at NVIDIA side. Overall, these methods can give you fast and accurate predictions, and it could be, say, 10,000 times faster than traditional methods. A similar work, including GraphCast and Pangu weathers, I think the ForecastNet happened in 2022 is one of the earliest work using machine learning model on weather forecast. Another example in collaboration with Stanford Group, led by Wenwen Ge, is carbon storage. So in many plants and factorizations, instead of release carbon dioxide into the atmosphere, we can store it under the ground. So it will carbon ice and become some kind of carbon rock that does not pollute the environment. But we need to simulate how the carbon dioxide migrate under the ground in this reservoir. Hopefully, it will not escape somewhere, but it will store here for a long time, like 30 years. So in this case, we will simulate this reservoir. The carbon will migrate under this reservoir. We have a 3D simulation with time. This is a multi-scale graph. We have several different injection wall, and we will have a finer mesh around the injection wall and coarser mesh overall other place. So in this sense, we can accurately simulate what happened around the injection wall. But overall, these models, when we go to 3D, it could be expensive and will require 80 gigabytes GPU to run such models. But still, it can be many times faster compared to numerical solvers. So in this case, it's 700,000 times faster than a numerical solver. And third examples are aerodynamic simulations on cars and vehicles. So this is a work we collaborate with NVIDIA against. So given different shape of cars, we want to model how the pressure fields evolve along the cars and find out the best design of vehicles. In this case, the input is car shapes and output is the pressure fields along the cars. And the end goal is to do inverse design to find out the best design of cars that minimize the drag and shear velocity. For this case, we use graph models plus Fourier models. We call it geometric informed neural operators. The basic idea is given any shapes, we're going to project into a latent space and evolve the physics on the 3D latent space. After we solve the pressure fields, we'll project back to the surface of the car. So such design is based on the underlying equations is evolving in 3D subspace. So we need to do 3D simulations. But we also have ongoing work that restricts the simulation to the surface itself. So instead of using a 3D latent space, also exploring using 2D latent space that will greatly saving computation times. So for this shipment cars and unharmed body trunk like datasets, overall the pressure simulation is quite accurate. There are some small error on the rigid parts like the bumper of the cars or wheels of the cars, but overall it's quite accurate. And for the general neuropaters, we also want to introduce a NeuroOp library as available on GitHub. There are several examples for Darcy equations, Berger equations. They are all in the notebook formats, very easy to run. So if you open the link, you'll find the notebook and they all can be run on, say, Google Colabs or locally. And this architecture is quite simple in the PyTorch formats. Basically, you just call the models and click and run through that. It's very easy. If we have some time, so we can do that together at the end of the talk. Okay, any questions so far?
No, good so far. Yeah, keep going.
Okay, thank you. Okay, so the second part, I'm going to talk about the recent work. One is the scale consistent neural operators. The general idea is to have one foundation operators that can learn for multiple scale and multiple type of equations. We understand that for partial differential equations, there are various different scales. For example, in the Poisson equations, we can have different type of inputs or different size of domains. For a small size of domains, the input could be more uniform, but for larger domains, the input will have a higher frequency in that. For the second rule, it is Helmholtz equations. In this sense, the small scale corresponding to a small domain or small wave number, and larger scale corresponding to a larger domain with many wave in that. Also, we have the famous Navier-Stokes equations. For small domain size or large viscosity, we have a small Reynolds number that with lower spectrums. But for large scale, for high Reynolds number, the decay of the spectrum is slow, and there's many Fourier captures. The motivation of this work is to have one universal models that can capture different domains or different scale of models. That we don't need to train a separate model for each of them. In Paris, say Fourier neural operators, when we consider different domain size or different Reynolds numbers, say for the small Reynolds number, usually they're given at lower resolutions, and the higher Reynolds number, they result at higher resolutions. But traditionally, if we will train one supervised learning models on each dataset separately, but in that case, we are not fully utilized data. We know that it is the same underlying equation governing all of these data sets. So we hope to use one models to train on all of these data sets and evaluate on all of these data sets. And because we know the underlying equation is the same, just with the different say viscosity parameters or Reynolds number parameters, it's more well-defined to have one models learning the solution operators of these underlying equations. For different size domains, we can do a simple change of variable, for example, y equals 2x, and plug it into the equations. In this sense, the change of scale of the model will just be equivalent to change the scale of the forcing and the some parameters. In this case, it is the Reynolds numbers. So the Reynolds number is a dimensionless parameters that is defined as the domain size times the average velocity divided by the viscosities. So if we change the domain size, it's equivalent to scale the viscosity, so the underlying Reynolds number remains the same. So in this sense, we just need to input the Reynolds numbers as an input, additional input of the models. If model gets information of the scaling parameters, it will be able to get the full information to correctly predict the solution outputs. So if we get the different scale inputs or different size domains, one way is to embed it into the Fourier space. When we do the Fourier transform, we know the underlying Fourier bases are, say, exponential 2 pi ik divided by L. If we just use standard Fourier transform, this domain length L is just equal to 1. But given different size of domains, we can put this domain length by changing the different input of the scaling parameter L. But of course, if we run the fast Fourier transform, we may not be able to directly size domain size. But this L, scaling L, is equivalent to scaling the frequency. For example, for the unit size L equals 1 and the frequency equals 1, If we're evaluating a larger domains, say domain size equals 2, then this k equals 1, l equals 2 is equivalent to k equals 2, l equals 1. Basically, we're grouping the frequency k divided by l together as the parameters we have for the weight matrix. So we can make the weight, the kernel weight, as a neural network depend on the scale and the frequency. We're learning a uniform, like a universal k can be applied on the corresponding position of the frequencies. So given different domain size or different range numbers, we'll put it as additional inputs, and inputs will be fed to the kernel matrix. In other words, the kernel matrix is conditioned on the frequency and domain length we have. Right. So the kernel of the Fourier transform, kappa, is parameterized by a function on the Fourier space f. And this function f is going to depend on the index, which is the frequency k, and the scaling parameter re here. So this re is equivalent to domain size L, or is equivalent to the viscosity mu here. So given these inputs, the model will get the full informations of the underlying equations, and it will have the capacity to predict for different equation given different Real numbers. For some machine learning considerations, we'll have this F as a neural network that has a position encodings similar to that position encoding in transformers. So this case reads to the I over C powers, where C is the total number of channel. And F is a complex network. So we're going to use complex activations, for example, complex GLU, basically do GLU on real part and complex parts separately. And another thing is that this F has channel square number of parameters compared to standard FNO models where we have a weight for each mode separately. In that case, it's n square, c square number of parameters. So this new embeddings can save quadratic number of parameters. The design is also similar to the transformer, where we have a three value key and curve matrix that is similar to the function kernel f here. So because we still use less number of parameters, we further develop hierarchy U-shaped architectures that have several network for the full solution operators. So on the low level, we have a kernel F that has less number of channels because we know that high frequency usually contains smaller amount of informations. So a smaller kernel F will be sufficient. And for higher levels, for the low frequency parts, we're going to use larger kernel functions R or F here. And overall, we are going to have, say, 3 or 4 kernel network corresponding to the high frequency inputs and low frequency inputs. Right, so after we developing the models, the scale consistency can also be used as a training technique to enforce the models and augment the data sets with different scales. So given a data set, usually at a fixed scale, we can rescale it and restrict to subdomains to obtain different scales. In this sense, even if we just get one data set with fixed scale, we can still learn learn the model of different scales. The algorithm is very simple. First, we do a rescaling, say for the domain size 1 with viscosity 1/1000. we can rescale to domain size of 4 with viscosity 1 over 250. And then we restrict to a subdomain of the rescaled inputs. This subdomain will have domain size 1 and viscosity 1 over 250. Its behavior will be similar to the datasets if we directly generate datasets of viscosity 1 over 250 with domain size 1. So basically, by using rescaling of the uniform size of domain and restrict to random subdomain, we can augment the datasets to get the different scale or say any scale smaller than the given scale. As another examples, for the Helmholtz equations, given coefficient and boundaries, we can again restrict to subdomains, and the consistency loss will be defined as the model evaluate on the large scale, and the model evaluate on the subdomain small scale. And because we know this is just a restriction of subdomains, so these two patch should match in the end. But one caveat is when we restrict to subdomains, the model may lose information from other set of patch. So we also given the boundary of the subdomain as additional inputs. So this boundary will correctly capture all the informations that is truncate out from the large domain. And taking one step further, even if we don't have the labeled data on the large domains, we can still enforce such a consistency loss. So we just randomly sample coefficient A and the boundary G, and we just enforce the model evaluate to the large domain should be equivalent to the model evaluate on the small domain. So in this case, the self-consistency loss become a self-supervision or say a self-trainings that even if we don't have a label data U, we can still train to enforce the efficiency, the scale consistency between the full domain and subdomains. But of course, this self-supervised loss should also be used along together with the data loss. For example, like I said, zero operators is one trivial solutions that have the same input and output as the large domain and small domains. So this loss can be only used to help to reduce generalization error, but it's not a complete loss that we can train without any data. Any questions so far?
Question. Give me a second.
Hi, I just wanted to confirm something. So you said that into F that you're passing the Reynolds number, right? Which is essentially scale invariant, some dimensionless quantity that's scale invariant.
Yes, so we're passing in the Reynolds number as additional input to the kernel.
Yeah, so for the Helmholtz equation, what would you pass? It can't be the Reynolds number. Or is it?
Yes. For the Helmholtz equation, we have the wave number k. I guess it's a different k, but it is passing into the equations.
Okay. So you want to pass in some feature that just captures the scale essentially.
Yes.
Okay, got it. Thank you.
Mhm. And this scale is intrinsically corresponding to the wavelength of the basis on the first space. So basically, we just scale the basis according to the domain length, which is equivalent to the Reynolds number or the frequency just by scaling change variables. Okay, so one part is the models with passing the scale parameters to inform the model of the underlying scale. Another part is as a training scheme, we can restrict to subdomain to gather different scale of inputs. And we have some numerical examples. For example, for the Darcy equations. So Darcy equation is basically divergence of A times gradient of U equals F. So in this case, for simplicity, we just assume the right-hand side forcing equals zeros. So just if we just scale the parameters, say we change scale y equals 2x, the underlying equation will remain the same. Right. So for this Poisson type equation, or say Darcy type equations, we don't have a scale parameters. So one models without scale parameters can capture all these different type of inputs, which is underlyingly equivalent to the harmonization of Poisson equations. Especially say it's different type of inputs, we can take in average of that, which still gives the correct outputs. Right, so on the Darcy equation, we can show that when using the data augmentation by restricted subdomains, the error reduced quite dramatically. We can get about half error compared to just training on the regional datasets. So it says that this scheme that using the data training can save a lot of parameters and a lot of training data. The second example is Helmholtz equations. We're doing a wave scattering problems. So we're given the coefficient, Dirichlet boundaries, and also the wave numbers. So we consider many different wave number, like 5, 10 to 100. So because this is kind of ill-posed problems, or says eigenvalue problems, it's possible that the input and output are different by some eigenvalues. The underlying data set is given by the Robin type of boundaries, so it's well defined. So if we're using the data augmentation scheme, it can correctly capture the training data from, remember, from 5 to 10 to 25. And they can also further generate to lower frequency numbers, say k equals 2 and 1. The error reduced by half for these two scheme. But trying to higher frequency is still harder. So overall, the methods so better advantage trying to lower frequency, but the high frequency is still unclear. And also the Reynolds number examples. So the data sets are generated on the unit one-by-one domains with different Reynolds numbers. But we're only given at one data set, remember 1000s, and we want to see how it generates to different Reynolds numbers from 200s to 10,000s. So in this case, we just train on Reynolds number 1000s, and we use the restrict to subdomains and self-supervised training by scalings. Overall, it shows that using these models with data augmentation by scalings reduce error for both lower range number and higher range number. Yeah, so this collaboration work happened at Caltech, sorry, it's a full line for work at Caltech and other collaborations. Thank you. So for the questions, there's a question by Chen Yang that, do you have preprints for this live work? So we haven't put this work on archive, but it should be out very soon.
Great. And then I think, Zongyi, you're coming second week of the hackathon or later half of next week?
Yeah, so I'm coming next Thursday on 18th or 19th.
Okay, great. Yeah, I think there's a lot of excitement around this. And of course, yesterday we had Max present on Poseidion. So there's a lot of very exciting things happening in foundation models for for PDEs. So very excited that you're all going to take that forward.
Yes, very looking forward to joining in person.
Yeah, and we have some good amount of compute resources allocated for this. So hopefully you all can run some good experiments during the time. Okay.
Yeah, thanks a lot for organizing it.
Yeah, great. Thanks, Zongyi. And then we'll take a 10-minute break, and then we'll start back at 11:30 for the last tutorial on vision transformers.